Hi, Trig Honors. So today we're going to talk about recursive formulas. So in the notes that we did for sequences, we went ahead and looked at arithmetic and geometric sequences and some sequences that weren't arithmetic and geometric, and we were basically looking for patterns. So recursive formulas are a little different. It's where you're describing a term in the sequence and you're comparing it to some other term. So as far as notation goes, we're saying that the first term, we could call that a sub 1. And then some particular term in the sequence, we would call that a sub n. And then a sub n would be minus 1 would be the term right before it. So let's say you had, for example, the first term, and then the second term, you had a third term, and then maybe way out here you had some term that we're going to call it the nth term. The term before it would be the n minus 1th term. The term after it would be the n plus 1th term. And it goes like that. So, for example, if I said n is 8, that would be the 8th term in the sequence. Okay, so if we're talking about arithmetic sequences right now, let's say we had something like number 1, where you're noticing that there's a common difference of 3. You're adding 3. Let's write that down. D is a common difference, where you're adding 3 to each term to get the next term. So that's the pattern. So you could say that any term in the sequence is equal to the term before it plus 3. And that is called recursive because you use this notation that says describe any term with the term before it or some other term in the sequence. So if I just give this rule to you, you would not be able to reproduce that sequence without some more information. So I would also have to tell you the first term, so you know where to start. And then I would also have to have that n is greater than 1 because, again, it would make no sense to say, and again, we're assuming integers for n because you can't have like the 0.5 term or something like that, and you can't have the 0th term or the -7 term. We're starting every sequence with the first term. Okay, so let's do another one. So for example, if I have 10 and then 0 and then -10, notice that we have a common difference of -10. You are subtracting 10, and that's going to go ahead and generate the sequence of numbers. You just keep subtracting 10. So any term is the term before minus 10. So again, if I just gave that to you, you wouldn't be able to generate those terms because you wouldn't know where to start. So I would have to say, well, the first term is 10. And again, n has to be greater than 1. Now, you could have also said n is greater than or equal to 2. That also works. And again, we're assuming integers. Okay, what about geometric? Geometric, so notice that you're multiplying or dividing by the same number to generate more terms in the sequence. So notice there is a common ratio for number 3. Let's write that down. R is the common ratio of 2, where you keep multiplying by 2 to generate more terms. So recursively, these are all recursive on this worksheet here. So if I want to describe this recursively, I could say any term is the term right before it multiplied by 2. So again, in order to generate the sequence of numbers, you would need the first term, which happens to be 2. And again, we'll have a little disclaimer there, n has to be greater than 1. So that is a recursive formula. What about this next one? Notice that you're multiplying by a third to generate more terms. That's your common ratio in this geometric sequence. So any term is the term before it multiplied by 1/3. So you could write it like this if you want, 1/3 times a sub n minus 1, same thing. And you could say that the first term is 4, and again, we'll say n is greater than 1. So that would be a way to describe this particular geometric sequence recursively. Okay, let's do another one. This one's a little trickier. So notice for this one, it's kind of hard to tell what's going on. Maybe you don't see it right away. It seems like I'm adding 2, and then I'm adding 4, and then I'm adding 2. It's definitely not arithmetic. It's definitely not geometric. But I think, well, you would be able to describe this recursively because if you take any term, you could take the term 2 terms before it and add 6. So notice this would work, but again, if I just gave you the first term, I don't think that would be enough information. I think I would also have to tell you the second term if you wanted to generate the sequence of numbers. So again, let's pretend we can't see this and let's give it a try. So this recursive definition here, it says the first term is 5. We have a recursive formula. The second term is 7. And then it says any term, so let's say n is 3. The third term is just the first term, so 5 plus 6 is 11. Let's keep going. Let's say n was 4. So if I want the fourth term, n minus 2, 4 minus 2 is 2, plus 6. So that would be the second term plus 6, which is 13. So do you see how, again, you could check more points, but this actually works. And again, our little disclaimer here, n has to be greater than 1. That was a tricky one. Okay, 6 and 7. It says find the first 4 terms. Okay, let's give it a try. So if the first term is 29, and this says any term is the term before it plus 10, so 29, 39, 49, 59, etc. Because if n is, let's write this down, if n is 2, if n is 3, a sub 3 equals, a sub 2 plus 10, etc. What about this next one? It says any term, we're going to let n equal 2, and we're going to find the second term. And according to my formula, it's the first. Got it. Okay, so we're going to say negative 4 plus 2 is negative 2. Let's keep going. So now if n is 3 and I want to find the third term, my formula over here says a sub n minus 1, so that's a sub 2 plus 3. So the second term was negative 2. So negative 2, that's 1. Let's keep going. If n is 4, a sub 4 is a sub 3 plus third term was 1. So 1 plus 4 is 5. Great job, everybody.